All right, so I'm going to talk about solving cubic equations. So I normally give this in a colloquium talk that lasts an hour, and I thought I would try it out here to see if I've been wasting people's time for 54 odd minutes. You'll have to tell me if it works. So cubic equations are the theory of elliptic curves, and it's an active subject in number theory. People have been solving equations for a long time. This is a Babylonian tablet that dates from the time of Hammurabi that was decoded by the great mathematical historian Otto Neugebauer, and it contains all these solutions of this Pythagorean triple equation in integers, and there are enough solutions on this amazing tablet, which we don't really know what it's about, to say that they had the general solution. So after quadratic equations come cubic equations, and the quadratic equations typically have an infinite number of rational solutions, but a cubic equation, like this one, can have a finite number, or like this one, can have an infinite number of solutions. And the central problem is to decide which is which. This is a picture of Pierre Fermat, who began the study, and one of his great observations was that if you took two rational solutions of a cubic equation and took the line through that, it would intersect the graph in one further point, because the equation is cubic, and that is also a rational solution. So by starting with the rather simple solutions of this cubic equation and taking the line through them and finding another, you can generate quite a few interesting solutions. And this equation has an infinite number of solutions because this process never comes back on itself like it does for the Fermat equation. And you'll notice that the rational numbers become quite large. Now, you might get the idea from this that the way you find all rational solutions of a cubic equation is starting with a very simple one. But even when the number of solutions is infinite, and here's a simple equation where the number of solutions is infinite, the simplest possible solution has x coordinate where the numerator has over 5,000 digits and the denominator has over 5,000 digits. And that's just the x coordinate. The y coordinate is larger. So to find this solution, which isn't too well documented, you'd have to have a good method. Now, the central theorem in the subject is due to Mordell and Weil. That's Louis Mordell. That's André Weil. And it says the set of solutions under this tangent chord process has the structure of an abelian group, and the key thing is that it is finitely generated. That's a fact about the rational numbers. It's always an abelian group, but not always that. And finitely generated abelian groups have the form z to some integer. That's called the rank, and a finite torsion group. When the rank is 0, you have finitely many solutions. When it's positive, you have infinitely many. That raises the question, what can the torsion group be, and what can the rank be? We know curves of small rank, but could the rank be arbitrarily large, for example? That would give us an idea. Well, the torsion was solved by my colleague Barry Mazur, who's in this picture, taken about the time that he started working on torsion in elliptic curves, and he proved that the only possibilities are cyclic groups up to order 12, and cyclic groups cause z mod 2, and this is in his famous paper that followed his work on the Eisenstein ideal. That's Gretchen, and this you may not recognize, that's Bernard Saint-Denis. And the record for the for the rank is now 28. That's held by Nohm. And well, we know the rank of this curve here, its coefficients, is at least 28. And here are 28 points with integer coefficients that generate a free subgroup of rank 28. We very strongly suspect the rank is 28 in this case. This was found several years ago, and no one's gone further. The main conjecture is due to Birch and Swinnerton Dyer, who made a guess for the rank based on the L function at 1. The L function depends only on the number of points mod p. Here they are on Birch's wedding day. Here's Brian, here's Peter. Peter was the best man. And this conjecture was made over 50 years ago and is still one of the central things in the subject. So I'm going to describe it. You take the number of points mod p, that's a finite number, and you write it as 1 plus p minus an error term ap. And then you define an infinite product by taking the product over all primes p of this. This isn't quite true, but it's close enough. It's true for almost all primes. And it's known that this product converges in a half plane in the complex numbers, at least when the real part of s is bigger than 1, 3 halves. But if you formally set s equal 1 in this product, and you just do it mindlessly, you get the product of p over the number of points mod p. And so if the number of points mod p is large on average, the product approaches 0. And when the rank of E is large over Q, you have a lot of solutions over Q, you'd imagine that the number of points was large on average. And that led them to this beautiful conjecture, that the function, first of all, has a continuation to s equal 1, so you can talk about its value at 1, that the order of vanishing of this analytic function is equal to the rank, and then that the leading term in its Taylor expansion is given by terms involving arithmetic invariance. We just had a beautiful talk on this in the number theory seminar. Well, the analytic continuation was obtained by Andrew Wiles and Richard Taylor in the 90s, and that was the key step in Andrew's proof of Fermat's last theorem. This is known, I should say, for elliptic curves over the rational numbers. There's also a conjecture for elliptic curves over imaginary quadratic fields where we know absolutely nothing. But at least you can evaluate now the L function at 1. And combining work I did with Don Zagier, and this is what Don looked like when I was working with him, with Victor Kolyvagin, we now know that if the L function is non-zero, the rank is 0, so the curve is finite. If the L function is 0, but the derivative is non-zero, that there are an infinite number of points, and when the order of vanishing is greater than 1, absolutely nothing has been proved. And I'm going to finish by talking about some beautiful work of Manjul Bhargava, who's made progress not on the rank of a given curve, but on the average rank, where you average over all elliptic curves over the rationals. This is a really interesting new idea, independent of the Birch and Swinnerton Dyer conjecture. And the first thing Manjul had to do to define an average was to enumerate the curves in a sensible way. So every curve can be written in this form where a and b are integers. He defines the height as the maximum of the two positive integers a cubed and b squared. There are clearly only finitely many curves with height less than a fixed real number. It grows like x to the 5/6 power. So letting x get larger and larger and larger, you enumerate all the elliptic curves. The average rank is defined by summing over the curves of height less than x, the rank, dividing by the number of curves of height less than x, and letting x go to infinity. If that limit exists, that's the average rank. We think it's equal to a half. No one can prove that, but he and Arul Shankar, his graduate student, have proved it's less than 1. And I want to thank you for listening to this insane talk. And some of these slides were prepared by William Stein, and I want to thank him for preparing the slides. Thank you very much.